In this video, we'll be going over a full stress transformation problem. This video is actually going to be broken up into two separate videos, so once you finish this one, just go on to the next one to finish up the problem. So we're given an initial stress state at point A, and we're asked to find the rotated stress state for the principal normal stresses, the maximum shear stress, and a rotated stress state at 40 degrees clockwise. And then after we find all those, we'll go ahead and solve for what the forces P1 and P2 are on the beam. So to start off, we'll just have to take our stress state and put it in terms of a stress block, just so we can start putting our coordinates together and put our Mohr circle together. So right now I'm going to draw what the stress block is going to be. So on the right here is what our stress block looks like given that stress state. So you can see we have along the x-axis we have 36.5 KSI in compression, since it's negative. And then along the x-face, which is perpendicular to the x-axis, going in the z direction, it's going in the negative z direction. So we have a negative 9.66. That's why it's going down in the negative z. And so once you have that one direction, you can figure out the direction of all the other shears along every face. And so that's going to be our stress block. Now we just need to find our coordinates that we're going to be using to plot our Mohr circle. So if we let's start with our x coordinate. So our first term is our normal stress. So our normal stress in this case is going to be a negative 36.5. And then our second term is going to be our shear stress along that face. And we're going to say that if it's rotating clockwise, if it makes the stress block rotate clockwise, then it's going to be positive. So that means that along the x face, it has a shear stress on it that causes a clockwise rotation. So that's going to be a positive 9.66. And then if we go to our z point, its normal stress is 0. There's no stresses acting on it. And then its shear stress that is acting on it is causing a counterclockwise rotation. So it's going to be a negative 9.66. So now we just have to plot that on our Mohr circle, which I'm going to draw just down here. We'll just use that. So here is our Mohr circle given the 2 points that we found. So we're going to be interested in finding these 2 points. That corresponds to our principal stresses. This is going to be sigma max, and over here is sigma min. We're also interested in finding the maximum shear stress, which is up here, tau max. Going to draw, so tau max is right over the center, and then so in order to find those angles, we'll also be interested in finding the angle it takes to rotate to those principal stresses. So this one, I'm going to call it 2 theta p, because every degree you rotate on the stress block on the Mohr circle, it's twice that. So that's one theta we're interested in. Another one we're interested in is how it rotates from here all the way up to tau max. We'll call that 2 theta s. So the first thing we got to find in order to solve this problem is just to find our center and what our radius of our circle is. So the center is defined as the first coordinate in each of our points, so negative 36.5 plus 0, that divided by 2. That'll give us what our center coordinate is. So when you do that, that comes out to a negative 18.25. And then our radius, that is defined, we can just use this triangle. If I draw it in purple, we're going to be looking at this triangle right here. So that radius that we're going to find is going to be, r squared is going to be equal to 9.66, which is the coordinate of our z point, squared, plus the coordinate of the center, which is 18.25 squared. So when you do that, you should get a radius that is equal to 20.65. So now that we got those 2 main points, we can go ahead and solve for what our sigma max and sigma min are. We can just solve that based off of these 2 guys. So I'll just change colors real quick. So our sigma max, that's just defined as the center plus the radius. So that's just going to be equal to negative 18.25 plus 20.65. So that'll get us 2.4. And then our sigma min is the center minus the radius. So that's going to get us a negative 18.25 minus 20.65. So that'll come out to a negative 38.9. So we got those 2 values. Now, and then if we want to find what tau max is, that's just going to be equal to the radius. So our tau max, our max shear stress, is just going to be equal to 20.65. Now we're interested in finding the angle that those act over. So the first angle we kind of want to find is going to be this angle right here. I'll just call that theta. So if we can find that angle, we can relate it to the other two angles we're interested in finding in. So for that theta, since we know those triangle distances, we can just say the tangent of theta is going to be equal to 9.66 over 18.25. So that's going to get us a theta which is equal to 27.9 degrees. So now we just need to relate that angle back to our 2 theta s and 2 theta p. So we'll start with 2 theta p. So you can see that 2 theta p, that's just going to be equal to whatever theta is. So we can solve that theta p is going to be equal to 13.9 degrees going counterclockwise. And then for 2 theta s, we can say 2 theta s is going to be equal to theta plus 90 degrees. So our theta s then comes out to being 97.9 degrees going in the same direction. So now we have our values for our principal stresses and our max shear stresses. We also have the angles that they act over. The only thing we got to do now is just put them onto a rotated stress block to show how they're actually acting. So I'm going to draw those down real quick. So here I have drawn the 2 stress blocks for the state of principal stresses and also for the max shear stress. So you can see we just rotated the principal stress one 13.9 degrees, and then we placed on there our sigma max and sigma min that we had found from the Moore's circle. And then for the max shear stress, we rotated it 97.9 degrees counterclockwise, and then we also put the tau max on each of the sides going in their respective directions. And also we had to put on a normal stress of 18.25 KSI, because that's where the point of max shear also has a normal stress applied to it. So that would be the answer for the first 2 parts. Now we have to move on to our third part, which is finding the stress block if we rotated it 40 degrees clockwise. So if we did that, we would go to our Moore's circle, and so we'd have to draw a new line that shows moving our 2 axis points to 40 degrees counterclockwise. So if we did that, they would end up somewhere about, they would end up somewhere over here, and then over here. So we'll just draw a line through that. So it would end up right there. So this is our, we'll call it our x prime and our z prime. So since we're rotating our stress block 40 degrees clockwise, 40 degrees clockwise on our normal stress block, that means on the Moore's circle, we're actually going to be rotating it 80 degrees. So that's what it's going to look like. And so now in order to find our new coordinate points for x prime and z prime, we need to analyze this triangle right here. So we're going to be analyzing this type of a triangle. So I'm just going to redraw that triangle just below so we can solve what that is. So it's going to look, so this is for our 40 degrees clockwise rotation. We are going to have our triangle that looks like this. We have our radius r, which we know, and then we're solving for our L1 and our L2 lengths. And then we also have this theta that we're going to be solving. We'll call it theta 1. So from the thetas that we know on our Moore's circle, we can solve for what theta 1 is going to be. And that's just going to be, we know that our pink theta that we had solved for, that plus 80 degrees, which is what we rotated through, that minus 90 degrees is going to be able to get us what theta 1 is going to be. So if we just look back up at that, we were saying, okay, theta plus 80 degrees minus 90 is going to be able to get us this angle, which is theta 1, which is the same as that theta 1. So that's kind of what we're solving for. Okay, so if we do that, you can get that theta 1 is going to be equal to 17.9 degrees. And so now we just can go ahead and use trigonometry to go ahead and solve for L1 and L2. So if you use your sine and cosines, you can get that L1 is going to be equal to 6.35 and L2 is going to be equal to 19.65. And so from there, we can use this to find what the coordinate points of our x prime and our z prime, and then use those to plot our stress block for that 40-degree rotation. So our coordinate for x prime, that is just going to be equal to the center plus L1. That's going to be our first term, and if you look back up at our Mohr's circle, we're saying that this point right here, our x prime, it's the center away plus our L1 term, which is the same term value that we found for this triangle is the same triangle up there. And then the second term is just going to be whatever L2 is. So that's going to get us a value of negative 11.9 and a value of 19.7. I'm rounding up to 19.7. I know we said it was 19.65. And then we'll do the same thing for our coordinate for our z-axis, or sorry, for our z prime. So this one is going to be similar. It's the center, but instead of plus L1, it's going to be minus L1. And then the second term is going to be a negative L2. So that's going to give us a negative 24.6 and a value of a negative 19.7. So now we just take that and put it on a stress block. So there to the right we have what our stress block looks like. Now we have our stresses figured out on each side. So you can see we have all of our normal stresses are in compression because we found them both to be negative. And then we have our shear stress going around the whole thing, which is 19.7 KSI. And then we have shown that it's being rotated 40 degrees clockwise. Okay, so the next thing we just have to do is solve for P1 and P2, and we'll do that in the second video.